Dear student, in this lecture we define positive set, negative set and null set and discuss some of its properties. Okay, so first we define, write down definition. Let x s mu be a signed measure space, a measurable subset E of x is said to be positive is said to be positive is said to be first positive set with respect to signed measure mu if mu of f is greater than or equal to 0 for each measurable subset f of E. Second, negative set with respect to signed measure mu if mu of f is less than or equal to 0 for each measurable subset f of E. And last one, null set with respect to signed measure mu if mu of f is equal to 0 for each measurable subset f of E. Okay, so we give some example. First example, let x is equal to closed interval 0 to 2 pi and mu of E is equal to integral over E sin x dx be a signed measure on x. Okay, first let E1, which is your closed interval 0 pi, which is a subset of x, that will be a measurable subset of x, is a positive set because mu of E1 is equal to integral over E1 sin x dx, and that will be integral 0 to pi sin x dx, and the value of this integral is 2, which is greater than 0. Okay, next we assume that E2 your closed interval to pi to 2 pi, which is also subset of x, is a negative set negative set because mu of e2 is integral over e2 uh, sin x dx, so that will be integral pi to 2 pi sin x dx, and the value of this integral is -2, which is less than 0. Next and the last one, let e3 is your closed interval 0 pi intersection pi to 2 pi, which is also subset of x, is a null set, because if we find mu of e3, this is integral over e3 sin x dx, and that will be uh, integral pi to pi sin x dx, value will be 0. So these are some examples of positive set, negative set and null set. Now we discuss one more example. Next example is, let x is equal to closed interval 0 1 and S your sigma algebra of Lebesgue measurable subsets of x. Okay, now we define a signed measure on mu on x. Mu is equal to m minus gamma mu of half, where m is your Lebesgue measure and mu at half is the point mass measure at the point half. Okay, now first we take a subset E1, which is your closed interval 0 1 minus half. Now this set E1 is a positive set. E1 is a positive set. Okay, for this because mu of E1 is equal to m of E1 and nu at half of E1, and you know m is a Lebesgue measure, so the measure of this E1 is m of closed interval 0 1 minus half and nu at half of closed interval 0 1 minus half. Okay, it is clear that the measure of nu at half is 0 because 1 by 2 does not belong to this set. Okay, and the measure of this is measure of 0 to half union half to 1. Okay, so union of these two sets are disjoint, so their measure is m of interval 0 to half plus m of half to 1 that will be half plus half, that will be your 1, so which is greater than 0. So your set E1 is positive. Okay, next let E2 is singleton set 1 by 2, so mu of E2 is equal to m of E2 minus nu half at E2. Okay, and the Lebesgue measure of singleton set is 0, so this will be 0, and 1 by 2 belongs to E2, so the value of Lebesgue, the point mass measure of the set E2 is 1, so that will be minus 1, less than 0. Next, we consider an example E3. E3 is your set 0 to half intersection half to 1, this set. Okay, now mu of E3 is m of E3 minus nu at half of E3. It is clear that E3 is empty set. Okay, so Lebesgue measure of empty set is 0, and this the point 1 by 2 does not belong to this E3, so the measure of point mass measure of E3 at half is also 0, so that will be 0. So your E3, this is your E2 is a negative set. Clearly E2 is negative set and E3 is null set. Okay, now come on to some remark is that every measurable subset of positive set is positive set. Okay, second, every measurable subset of negative set is negative. Okay, and last one, every measurable subset of null set is null set. These null set, all these three follows from directly from the definition, so there is no need to prove of these three. Now we trying to prove proposition is first every not every, it is countable union of positive set is a positive set. Okay, means the count, if it have a sequence of sets and take the count their union, means that countable union, so that countable union is a positive set. Next, countable union of negative set is a negative set. Okay, last one, countable union of null set is a null set. Okay, now we prove first, and second and third are exercised to you, so we proving first. Let an be a sequence of measurable subsets, measurable positive subsets of X. Okay, what we prove? We prove to prove that union n is equal to 1 to infinity an is a positive set. Okay, so for proving this, uh, let E1 is equal to E1, E2 is equal to A2 minus A1, E3 is equal to A3 minus A1 union A2. Okay, and so on. En is equal to An minus A1 union A2 union and so on union An minus 1. Okay, so we observe that En is intersection En intersection Em is equal to empty for n not equal to m. Okay, means all these Ens are pairwise disjoint, and union n is equal to 1 to infinity an is same as the disjoint union of Ens, n is equal to 1 to infinity. Okay, so it is clear that your all these Ens are positive sets. Okay, so uh, uh, let f be any measurable subset of union n is equal to 1 to infinity an. Okay, then this f can be written as f intersection union n is equal to 1 to infinity an, and that will be same as f intersection n is equal to 1 to infinity an, and this will be your disjoint union of f intersection n. Now f is measurable set, so first we find the measure of f. Mu of f is same as mu of n is equal to 1 to infinity f intersection en, and that will be your summation n is equal to 1 to infinity mu f intersection en. Since en is a positive set for each n greater than or equal to 1, therefore f intersection f intersection en is a subset of en, and this f intersection en is a positive set. F intersection en is a positive set. That is mu of f intersection en is greater than or equal to 0 for every n greater than or equal to 1, and hence mu of f is greater than or equal to 0. Thus your Hmm. Countable union. Countable union of positive set is positive set. Okay.